Hello engineers, welcome back to another video. In this video, we are going to discuss path planning for robots using an algorithm called A star. In addition to that, we're also going to discuss related algorithms like the Dijkstra algorithm and the greedy search algorithm. In the problem of path planning, a robot is required to plan its path that starts from the position where it is right now to reach a goal position that is given by us or by the system itself. First, let us see the visualizations of these algorithms on a simulated robot. All right, so we are going to run our path planning algorithms on a ROS-based simulation. ROS stands for Robot Operating System, and it is a framework to develop, create, and test robot software. In ROS, we can create various different simulations of different robots and test our different algorithms on those simulations. For our case, we are going to test our path planning algorithms on this particular simulation that you can see over here. In this simulation, we can see that we have a hexagonal room with the walls. Also, we have these 9 cylinders that are present in the simulation as obstacles. And we can see our robot that is present over here. Let's have a closer look at the robot. As you can see, this is the TurtleBot3 robot. It is a two-wheel drive robot that is used for education as well as research. This robot is equipped with a LiDAR sensor along with a camera. We can use this robot to do various autonomous navigation tasks like mapping, localization, and most of all, path planning. Now, the window that we can see to the left over here is the RWiz application. RWiz is a 3D visualization software for ROS, which is used to visualize the different data and the algorithms. We are going to use this RWiz to visualize our path planning algorithm. First, let us see the working of the Dijkstra algorithm. So we set the goal position over here. So as we can see, the robot is now working out to find a path that starts from this start node and ending that to the goal node. It's going to take some time, so let us see how that finally works out. The robot is now really close to finding the goal node. Let us see what happens when it finally finds the goal node. As we can see, once the robot planned its path from the start to the goal node, it followed that path and started from the start to reach the goal node. Now let us see the working of the greedy search algorithm. Let us set a goal node for the robot and see how it plans its path. And finally, let us check out the working of the A star algorithm. Let's set a goal for the robot. Now, looking at the three visualizations, you would have a basic idea of how the robot is planning its path. In the case of Dijkstra, the search for the path was in a breadth-wise manner where the robot was searching a broader area. In the case of Greedy and A-star algorithm, the search was quite directed. It was only focusing on reaching the goal. So let us discuss the technical details of these algorithms to understand their difference and their behavior.
One really interesting application that a lot of cool robots need to perform is of path planning. Path planning is a computational problem where we are required to find a set of valid configurations or states that take the robot from the start position to the goal position or state. Be it a mobile robot like the TurtleBot or a quadruped robot like the Spot or even a manipulator robot like the KUKA robot, all of them need to perform this path planning operation. That is, starting from the start position, need to find a path that goes to the goal position. Usually, we also need to add certain constraints to the path planning algorithm to make it adjust to the real world environment. If we add a constraint that we need to find the shortest distance path from the start to the goal, we have a problem called the shortest distance path planning. One such really popular and efficient algorithm is A-star. A-star not only finds the shortest path as well as it does it in a very short amount of time. Historically, A-star was first developed for the Shaky Robot project built by the Stanford Research Institute. Alright, now to understand the A-star algorithm, first let us discuss how a general path planning algorithm works. Mathematically, the path planning problem is solved on a graph. A graph is a mathematical structure that consists of nodes and edges. The nodes represent a robot state. It can be a position or a motor value, and the edges between them represent that we can go from one state to the other state. Let us consider this example over here. In this graph, we are given different nodes. Two of the nodes are already decided, which are the start node and the goal node. We can only move between the nodes which are connected by the edges. Now the path planning problem is that we need to find the set of nodes and edges that we can follow starting from the start node to reach the goal node. Considering a general case, we can number the nodes starting from 0. In our example, we have numbered the start node as the 0 node. As a first step, we retrieve all the neighboring nodes from the start node, as we can see over here. We retrieved the nodes numbered 1, 2, 3 that are connected to the start node 0 by the edges. We calculate the function f for these three nodes. The f values are f1 is equal to 1, f2 is equal to 2 and f3 is equal to 3. The function f over here can represent any distance metric that is related to our problem. For a navigation example, the function f can either represent the distance from the start node or it can represent the distance left to be covered to reach the goal node. Or it can either be a combination of the both. As we progress with the video, we will see that the function f is what determines the behavior of the complete path planning algorithm. After expanding based on a problem definition, we can either start expanding the nodes based on the minimum f value or the maximum f value. For our example over here, we are going to expand and find the minimum f value. Hence, in this step, we select the node 1 as our next expanding node. As we can see in the next step, the node 1 is expanded further along its neighbors. We get two more neighbors which are 4 and 5. Accordingly, their function values are also determined. We can see that f4 is equal to 1.5 and f5 is equal to 5. From this state of the graph, we can see that the next node that we have to expand is 4. Hence, in the next step, we are expanding the node 4, as we can see over here. On expansion, the node 4 leads to a neighbor node, node 6, which has a function value equal to 6. Again, considering this state of the graph, we select the minimum f value, which is corresponding to node 2. As we can see in the next step, node 2 is expanded to the neighboring nodes 5 and 7. Similarly, as we keep on going through this process, eventually when we reach the goal node, as we can see over here, we can use backtracking to determine the path starting from the start node to the goal node. Based on the expansion, we can see that the nodes 0, 2, 5, 9 lead to from the start node to the goal node. One particular edge case that we also have to consider is something over here. Consider the example of node 5, which is connected to node 1 as well as node 2. As we can see, node 5 was expanded based on the node 1. And its f value was also calculated according to 1. Let us assume that the value of node 5 from node 1 is 5. However, as we expand through the graph, we see that node 2 is also connected with node 5. Let us consider that the f value of node 5 from 2 is 4. Hence, in order to maintain the shortest expansion, we are going to change the f value of node 5 to the minimum of the two, which is 4. Also, while backtracking, we are going to ensure that node 5 backtracks to node 2 rather than 1. So this is an edge case that we also need to consider while running a path planning algorithm. In a real world environment like for a robot, we are usually not given graphs. However, what we are given are maps of the environment. In a map, as we can see over here, we are given the start position and the goal position along with the different obstacles that we need to avoid. In order to convert this map into a graph, we overlay a grid over that map. One of the cell of the grid is going to represent the start position and one cell of the grid is going to represent the goal position. We are also going to mark the obstacles in that grid map as well. The cells of this grid can be considered as the nodes of the graph and the neighbors of any general cell, as we can see over here. These cells will be connected by edges. Hence, from a graphical perspective, at any point of time, a robot can only move to its neighboring cells. Once a path planning algorithm has found a set of cells that the robot can go through to reach the goal position, a different path following algorithm can be employed to follow that path. As we said before, the choice of function f can determine the behavior of the complete path planning algorithm. If we consider the function f to represent the distance from the start state to the state under consideration, and we give equal value to all the neighbors, we have a search method called the Dijkstra search. Particularly in this, the path expands in a more broader manner, as we can see over here. The nodes will be expanded in such a way to find the optimal shortest path. If we consider the function f to represent the distance from the state under consideration to the goal state, then we have a search called the greedy search. In a greedy search, the path searching will be in a very directed manner, as we can see over here. The nodes will be expanded in such a way to find a path in the shortest possible time. However, the path that we found will not always be optimal. The A star search combines both of these search methods. For A star, we consider the value of f to be the sum of distance from the start node and the distance left to be covered to the goal node. It combines the direction of the greedy search and the breadth-wise approach of the Dijkstra search. The nodes are expanded in such a way that they not only find the optimal shortest path, but also in the shortest possible time. Now, considering a real-world environment, it may not be always possible to find the value of the distance from the node under consideration to the goal node. In order to represent that, we use what is called a heuristic function. The heuristic function approximates the distance from the node to the goal node. In order for the A star search to work in the most optimal manner, the heuristic function should satisfy some properties. In bare minimum terms, the heuristic function should not overestimate the actual distance and should be consistently decreasing. These two conditions on the heuristic function ensure that the A star search will proceed in the most optimal manner. Alright, so this is it for the technical discussion related to the A star search algorithm. Now let us have a brief look at the code.
The code we are going to discuss over here is uploaded on GitHub. The link to that would be in the description box below. First, let us have a look at the Dijkstra algorithm. At the start, we initialize various different lists. The open list contains the nodes that are going to be expanded. The closed list contains those nodes which have already been processed. Parents is used to store the parent of each node so that it is easier to backtrack the complete path after we have run the complete algorithm. The G-cost dictionary over here stores the distance from the start node to the node under consideration. As a first step, we add the starting node to the open list. And we keep on looping on the open list until it is empty, or we break the loop when we have found the goal node. In order to select the lowest G cost, we sort the open list over here and select the lowest value. Computationally, this operation over here is the one that takes the longest amount of time, and it will take a longer amount of time as more and more nodes get into the open list. In order to speed the computation up in this part of the code, we can use a data structure that goes by the name of priority queues. Priority queues store the elements already in a sorted format so that we incur less computational cost when selecting the minimum node. We add the current node to the closed list so that we do not visit it again. This grid whiz part over here is for the colors that we were seeing in the visualization window. Here is the break condition if we have reached the goal node. After all the checks and initializations for the current node, we find the neighbors of the current node. We iterate over those neighbors to expand over their nodes. If the neighbor is already in the closed list, then we do not process it. First, we calculate the f function, which is just the g cost over here. Then, if the neighbor is present in the open list, we first check if the g cost we just calculated, is it less than the one that we already have stored in our set structure. If it is less, then we update the g cost. Otherwise, if the neighbor is not present in the open list, then we append that to the open list. Once the above loop has completed, we backtrack to find the path starting from the start node that goes to the goal node. We are easily able to do that using the parents list that we initialized earlier. Finally, we return the shortest path that we found. Now let us have a look at the greedy algorithm. The structure for the code is exactly similar to the Dijkstra algorithm. However, over here, instead of using the G cost, we use the H cost. The H or heuristic over here is the Euclidean distance from the current node to the goal node. Euclidean distance is usually the best distance metric that we can take for such path planning algorithms, as it most of the time underestimates the actual path. Similarly, over here, when we are expanding the neighboring nodes, we are calculating the H cost instead of the G cost over here. Rest of the algorithm is completely similar to the Dijkstra algorithm. Now let us have a look at the A star algorithm. The code for A star is exactly similar to the Dijkstra's algorithm. However, in this case, we calculate the F function using the sum of the G and the heuristic function. As we can see over here, we are first calculating the G cost, then we are calculating the heuristic, and finally, we are evaluating it using the F cost, which is a sum of G cost and H cost. Rest of the code is exactly similar to the Dijkstra algorithm. All right, so this is it for the discussion related to the code of these three path planning algorithms. And also, this is all what we had to discuss in this video. If you like the video, press the like button and subscribe to the channel for more such videos. And thank you for watching. Bye.